Now the next exercise is to find out the center of mass of a uniform semicircular plate or a disc. Now this is a plate, not a ring, not a one-dimensional body, but a two-dimensional body. The mass is now distributed over an area, right? So if we want to find out the center of mass of this disc, means we want to find out the position of that one point, that single point where all the mass of this disc can be assumed to be concentrated to work mathematically. So in order to do that, what we do is, once again we take the horizontal axis here as the x-axis and the vertical axis passing through the center of the disc as the y-axis. Do we all anticipate once again that the center of mass of this half disc will lie on the y-axis? That means its x coordinate will be 0. Why so? Because if you look at the symmetry of the figure, the amount of disc that we have on the left side of the y-axis, we have the same amount of disc on the right side also. Isn't it so? So we expect that the center of mass of this whole body will come out somewhere on the y-axis itself, somewhere over here. Let us check that. We can always verify, isn't it? Now, how do we find out the center of mass? To do that, once again we have to divide this disc into some elements, some small mass elements whose positions we can find out, and then we can use those positions to find out the integral for the x coordinate as well as the y coordinate. Now see here that in case of a half disc, we can use the result of a half ring that we have derived in the previous exercise, where if we consider a half ring, let's say like this, having a certain radius r, okay, and if we consider a small thickness of this ring also, like this, such that we get a kind of a small ring of radius r with a small thickness, and we can consider this thickness as dr. Okay. Now, do we from the previous exercise know where the center of mass of this half ring lies? Do we remember this formula that the y coordinate of center of mass of a ring, half ring actually, is 2r by pi, where r is the radius of the half ring, isn't it so? So we can use this result to find out the center of mass of this half disc also. So it is this result that we shall be using here. So for this small half ring that we have considered as our element, we need to first find out its mass. What is its mass? How do we find out the mass? See that here on this half disc, the mass is distributed over an area, right? So we first define something that we call as the mass per unit area of this half disc. There is a notation that we use here, just as in the case of a one-dimensional body, in case of rod we discussed lambda as mass per unit length. Here we use the letter sigma to denote mass per unit area. What will be that here in this case? If the mass of the disc is capital M and if its radius is capital R, do you see that the total area of this half disc will be pi r squared by 2, half of the area of a circle, which will be 2m by pi r squared, right? So this is mass per unit area of the half disc. And now in order to find out the mass of this elemental ring, half ring, we need to find out its area, this shaded area in white we have to find out. How do we find out this area? See that we can find out, if we call this area as dA, this area is nothing but the area of the semicircle of radius r plus dr, and subtracted from that the area of the semicircle of radius r. Isn't it so? So there is this ring with inner radius r and outer radius r plus dr, right? This is r, this is r plus dr. If we find out the area of the half ring or half semicircle of radius r plus dr, and subtract from that this area, the area of a semicircle of radius r. Do you understand? We'll get this area, the remaining area will be this one. So this is what we are going to do. So what is the area of a semicircle of radius r plus dr? It will be nothing but pi r plus dr whole squared divided by 2, right? Subtract from that the area of the semicircle of radius r, which will be nothing but pi r squared by 2, right? Now what we do next is we solve this. Pi by 2 we can take outside, and inside the bracket let us open up the square to get r squared plus 2r dr plus dr squared, and then there is a minus r squared in the second term, so minus of r squared. See that the plus r squared and the minus r squared will cancel out, and out of these two terms that we have, 2 times r dr and dr squared, understand that dr being a very small value, when we do dr squared, that means dr into dr, that will be an extremely small value, isn't it? It's like when you multiply 0.01 with 0.01, you get 0.0001, which is an extremely small value. So we say that this value dr squared can be neglected in comparison to this particular term, which contains only 1 dr. Okay, so when we neglect this, see that what are we left with? We are left with pi by 2 into 2r dr. This is all that we are left with. This is an important step here, understanding which terms can be neglected, right? Because that will help us do the mathematics of such exercises easily. See that in this case the 2 cancels out, and we are left for dA. What is the value of dA? dA will come out to be pi into r into dr. This is the value of the area or small area of the elemental ring that we have considered. Now see that this expression once again is an important expression, and we can in fact understand how to get this expression without doing this whole exercise, because it takes its own time. If we understand how we can get it directly, we need not do all this exercise. So how do we get the value pi r dr directly? Go back to the figure once again. See that this ring that we have considered having a radius r and a thickness dr, if I draw it here once again, let's say this is the half ring of radius r and thickness dr. This is the thickness which is dr. Do you understand? It's like a strip which is curved in the shape of a semicircle, right? Let us straighten this strip. If we just straighten this strip, what will be the length of this strip? By the length I mean this particular length. Do you see it's a semicircle of radius r? So its length, this length will be pi r, whereas its thickness over here will be nothing but dr, this thickness that we have considered here. Now what we get here is a rectangular strip of length pi r and thickness dr. What will be the area of such a strip? dA. Can we say that the area of a rectangle is length into width? So the length here is pi r, whereas the width is dr. Do you see that we are getting the same value as we have obtained here without doing all this exercise, right? So this is one standard way that we can use to get the areas of small elements. We shall be using this particular process later on also in other exercises also. So understand that we can always consider the small area as the length of a certain portion of the area multiplied by its thickness, length into width. This always gives you the area. Okay, directly we can use this. So this is what we are getting as the area now, the small area dA, and sigma, the mass per unit length, also we have obtained. So now we can we say that the mass dm of this element will be nothing but mass per unit area, which is 2m by pi r squared, into dA, the small area of this ring that we are supposed to find out. So 2m by pi r squared into pi r dr. Pi will cancel out and we shall be left with dm is equal to 2m by r squared into small r dr. This is what we are getting for dm. dm, the mass of the elemental half ring. Now what do we do next? Next we find out the center of masses of the x and the y, like the center of mass along the x and the y axis. So x coordinate of the center of mass by definition is 1 by capital M integral of x dm. Understand that this is a half ring. The element that I have taken here, the element that we have divided this half disk into, is a half ring. And for a half ring, the mass, the entire mass of a half ring of radius r can be concentrated at a position of 2r by pi along the y axis, right? Whereas if you remember, the x coordinate of the center of mass of the half ring comes out to be 0, right? So can we say this half ring that we have considered here, its x coordinate will lie at x is equal to 0. So this x will be 0 over here, so that the expression for the x coordinate of center of mass itself will come out to be 0. Which we were expecting actually. We were expecting the center of mass to be lying along on the y axis. That means the x coordinate will be 0, which is as it is coming out to be. Now what about the y coordinate of center of mass, which by definition is 1 by m integral of y dm. What is the y coordinate of this elemental half ring? Can we use this formula that we have derived in the previous exercise? We say that for a elemental ring of radius small r, its center of mass itself will lie at 2r by pi from the origin, from the point O, into dm. dm we have just now calculated. It is 2 times capital M by capital R squared into small r dr, right? So this is the integral that we are supposed to solve, and we have to put the limits also. What will be the limits of integration? Do you see that here our half ring, as we take up different half rings, this half ring we have taken for a radius r, then we will take a bigger half ring of a bigger radius, then a half ring of a greater radius, and finally we will reach the half ring having a radius which will be equal to capital R. And what will be the smallest possible radius? The smallest possible half ring that we will have here will be the half ring which will have a radius which is almost 0. So as we move from small r is equal to 0 to small r is equal to capital R and consider half rings, we will be able to cover the entire half disk, right? So can we say the limits of integration here should be 0 to capital R for the small r value. Small r is the integrating factor, right? Now we can solve this. See that m cancels out and the constants we can take outside. So 4 by pi capital R squared comes out, and inside the integral we are now left with, there is a small r over here and there is a small r over here. So we will have r squared into dr, limits from 0 to capital R. Solve this. 4 by pi r squared into integral of r squared dr will be r cubed by 3, limits from 0 to capital R. Put the limits. 4 by pi capital R squared into capital R cubed by 3 minus 0, so which will be like this itself, and r squared will cancel out with r cubed and we are left with 4r by 3 pi, which is our final answer for the y coordinate of center of mass. Another important expression for the center of mass of a half disk, right? Another relation to be remembered, another relation to be directly used in other questions. So 4r by 3 pi, once again if we look at this factor 4 by 3 pi, it is certainly going to be less than 1. So that makes us understand that the y coordinate of center of mass will be less than, at a distance less than r from the origin. So somewhere over here we expect the center of mass to be, rather slightly down only, because more mass of the half disk is in the lower portions, right? So slightly over here, this will be the position of the center of mass at a distance of, this distance here is 4r by 3 pi.